So, hi, I'm Philipp. Today, I want to show you how log management is working from grep to full text search and back, and maybe like the combination of things. So let's dive into that and see where we stand or what you can do around that. So one thing that I sometimes think about or feel is that technology is often moving in one way, and then it's kind of taking like a counter move. So it's kind of like going the opposite way, or we have basically reached the pain point of one area or one specific thing. And then kind of like the pendulum swings back to the opposite, just because we want to have a new set of pain points and problems. And one area where I have experienced that in the past, just to kind of like lead you more gently into that topic, was the going from fat client to something cloud-based and all the steps before that. So back in the days, that was rather before my days. Maybe some of you still were in those days where you had the mainframe, which was the central unit. And then you had like the dumb terminals that were just connecting to that. And they were basically just like the IO or interface to the mainframe. So you had all your resources very much centralized. And then that was kind of like not what everybody wanted, or like that kind of like went as far as it could at that point in time. And then the pendulum swung like the other way, where we basically ended up with personal computers, or sometimes called fat clients, heavy, rich, or thick clients. I don't want to make the differentiation here, but here then, rather than having everything, all the data and all the access in a central place for everybody, everybody would get their own personal desktop computer or whatever to keep your data, and you wouldn't need a network, and the central server could go down. So it had advantages, and it was faster in some ways, and it didn't need all those big central resources because everybody had their own single box and was much more separated from the rest. And then people kind of didn't want to be separated or stuck in their own little box anymore. And then we kind of swung the other way around again, when we went to thin clients. Maybe those of you a bit older remember that. I remember when I came to university, I didn't have a laptop at first. And so I would use the computers provided by the university. And yeah, they were using WebEx or some other bad technology that took forever to start up. And it was still an interesting approach, because you had like, you can load all the resources from one central place and you can use them on any computer that you have there. But it was still not the ideal experience. So moving on a bit further, then at some point, everybody got their own laptop, and nobody wanted to use those thin clients anymore because they were slow and not as customized, and you didn't have all your data there maybe. So you would then have like your own data that you could carry around with you anymore. So we had left behind the desktops. Now we could carry the data with us and be more mobile, without having the craft of having the thin clients or having some server client application. And yeah, maybe you had a modem and you could access some data, but that still wasn't that much fun. And then the kind of like the counter move again was then, nowadays, I don't want to say everything, but a lot of stuff is in the cloud. So then your laptop or Chromebook, for example, is more like a thin client anymore. So it's this constant going back and forth. Like, you want to centralize everything, then you reach a pain point. Then you want to decentralize and give people like offline data and have it locally. And then it swings back again to centralizing and providing more services. This is often driven by better products, or also like innovation in terms of architecture and resources that are just available. So it's like you go as far as some technology takes you, and then kind of like the pendulum swings the other way, and then you go the other extreme or other approach, and then you go to that. And this is where I want to go with logs a bit as well, that there are multiple approaches, and it's kind of like that there are different swings of how you can approach something and what their trade-offs are. And enough about thin clients and fat clients and everything. Let's go to our actual problem, the logs. So the main point here is that your requirements and your trade-offs generally change over time, or maybe in a less nice way to put it, like your pain points might also change over time. It's like once you hit something and it becomes very painful, you want to trade that pain for some other pain. Like there will always be some limitation or some pain point, but either the grass on the other side is greener, or you just want to get rid of one specific pain point and would be accepting of some other limitation or pain point and would trade those. And that's kind of like how often these technological decisions or movements work out. At least in my mind, it's very much like you hit one end of the road and then you swing back until that other road continues further, and then you can swing back to that. So let's dive into logs with that. So why am I even talking about logs? I'm working for the company Elastic, the company behind Elasticsearch, Logstash, Kibana, Beats. Maybe you know the Elk stack, maybe you have used it. We do a lot around logs, not just logs, but also other things. But logs are very core to what we do or think about. So in this talk, I'm trying to map out a bit like how did we get here where we are in terms of what are common solutions, and also what is kind of like the way forward, or what are some of the things that people work on, or kind of like the pain points that people bump into, and we want to solve them as we go further. So log management is, as we have discussed in the intro already, you have a lot of logs and it becomes at some point painful. So oftentimes you start with just running tail on your logs, or maybe you run less plus capital F. If you've always used tail-f on the file, use less plus capital F, because that one basically you are in less with plus F, you're live tailing. With Command C, you basically break out of the live tailing, and then you can move up and down in your log. And you can also search with just a /. You can just search in that log file. So it is a bit less painful than what you get with less. Because you don't have, with tail F, you always need to kind of like, once you want to go back up in history, you always need to jump out of that tail F and then open less to search for something, or then you run grep or whatever. With less plus F, you can have everything within less, which is maybe a bit nicer. But that still doesn't solve the problem if you have this very large log file that we have talked about before. You're the little submarine and you're trying to find something in that big log file. And with less or tail, maybe that is not as much fun as you would wish anymore. So then what many people do is they reach for grep and try to make more sense out of their logs, and probably throw in some shell scripting as well, or some more advanced features of your shell to just work for that. So I assume most of you are familiar with that one. So we're grepping for anything with an error, and we assume it's not case insensitive because we're just looking for uppercase error in var log error. We sort those by occurrences. We only take the unique lines, but we sort them by, or we count the unique lines and we sort by the occurrence, and we take the top 5. So basically we're searching all the errors and we're getting the top 5 most common errors sorted by how often they appear. And that is what this would output here. So this is just a very quick way to maybe make sense out of this 7 GB log file, just to run grep, to understand what are the common errors, how many times do they appear, what are they, and then you probably need to slice and dice deeper in your data. And that works to some degree. The problem at some point though is if you have an application that is either a microservice or at least a distributed application, or something that you scale up and you have more than one server, grepping through one log file is not enough anymore, because suddenly you maybe have 5 servers and you need to search across all of them. And yes, you could SSH into 5 different servers and run the grep command on all of them. And then you try to look through all the 5 windows that you have open to find what you're looking for. But that's probably not super structured. Or you could have some approach where you try to download all the log files and centralize them and grep through them in one place. But all of those are kind of like only like bad hacks or supports that you try to cobble together, but it's not really a proper solution. Also, if you use something like Docker or Kubernetes, where data is, or the logs are ephemeral, like the container just appears and disappears, You probably don't want to have the problem that you basically need to chase logs quickly after they have appeared, because otherwise they might just disappear and you might never find those errors anymore. So grep is nice, but probably you want to have a more centralized solution to get to your logs. And one of the ways to get there that has been around for quite a while, and especially in the enterprise is very widely used, is Splunk. And I'm definitely not a Splunk expert. So if you have any comments on that, jump in and help me learn something as well. But just for the general architectural way of how data works here is you have a log forwarder. So you can centralize all your logs from whatever containers or servers or distributed data centers you have. You have those peer nodes where we store the actual logs, and then we can replicate the data between them as well. And then we have the search head, which is basically the interface from where you can search. And that structure works very well to centralize your logs and then search through them. To query, Splunk is very good at providing an interface that is kind of similar what you have used from the shell. So you will feel pretty much right at home here. So you can say the source is my error log, and then I'm just doing a regular expression and just search for anything that contains a fatal error. Or I'm looking for the Nginx access logs. I'm getting the top 1000 results, and then I extract the top 50 client IPs out of that. So you can extract a lot of those pieces of information in a way that is kind of similar to what you were using with grep before, but it is centralized now, and you don't need to worry about on which server is that, or will that disappear when a container goes down or it gets replaced. So that is quite a big advantage already. Generally, the way that the data in Splunk is stored is you have an event index, which is pretty minimally structured. So it has extracted some fields. For example, I think the file name is commonly extracted, or the server where this is coming from. And you can then search through those pretty quickly because they are explicitly extracted. But the rest of the querying you do at runtime, which is nice because you don't need to annotate or parse all your fields, though you can extract fields that you think you want to search through commonly. The downside is doing that query time searching or extraction of features is a bit more expensive. So your searches will get slower. Generally, Splunk is very good to get your recent data. And then if you search very large amounts of data, it's basically like you can basically watch it as it backfills or finds the older events that you have been searching through. If you have more of a metrics use case, there is also a more highly structured data structure for showing metrics and building a dashboard out of that. But for events, it's generally minimally structured, and then you can at index time extract the fields that you think that are relevant and you will search for frequently. But a lot of the features are to extract stuff at query time, which will be slower, but it makes you don't have to parse it up front, and you don't have to pay extra time in parsing or disk space or whatever. So it is kind of convenient to work with that. The problem is, like I said, speed can be an issue if you do all those features at query time, and Splunk is a commercial tool, so it can get pretty expensive quickly. So a couple of years ago, then the famous ELK appeared. So you have Elasticsearch, which stores the data, Logstash, which was kind of like the ingester or parser and enricher of events, and then Kibana to visualize that. In Splunk, you had like that query interface or search interface that was kind of like the equivalent here. Logstash is the thing to potentially get your data or accept your data, and then you can parse and enrich it. When I say parse, I normally mean, let's assume we have an Nginx access log. We could extract the HTTP verb, so it was a GET, and we know the IP address. And we parse all of those, and we also find the right data types for all of those. So one thing that the ELK stack or Elasticsearch then in the background, which stores the data, is very big on, is extracting all the individual fields finding the right data type, storing it correctly, and it will then make your queries much faster because you basically spend more time on the pre-processing or the indexing, and that makes your searches much faster afterwards. One thing that people are sometimes confused about or ask us about is, why would I use full text search for logs? Like, I get it. Elasticsearch is widely used for search. So you have it if you search on Wikipedia, GitHub, Stack Overflow, behind the search box, for the full text search problem, there is Elasticsearch doing the search. Why would I use that for my logs? Isn't the Splunk approach much saner and it's kind of like more grep-like? Well, maybe or maybe not. So the way we see it is that logs are pretty much a search problem, because storing the logs is not the relevant or interesting part. What you're interested in is finding the right stuff quickly in your logs. So by extracting all the fields and preparing your data, you have it much easier afterwards to work with that data, because you can rely on specific data types. You can more easily do like IP ranges, or you can search for a specific HTTP verb by just filtering down on that, or you extract the response codes and you can filter down on those response codes rather than having like a more grep-like interaction with that. So you can have those explicit fields extracted and then work on those individual fields. Which brings me to the data structure behind that full text search uses. So if you have, we'll just stay with the text here, but this could be a log message as well. Basically, what you do is you have a sentence like winter is coming, and then you tokenize that. So you basically break it up on the white spaces or punctuation marks, and you extract the terms winter is coming. And then what you can do is you basically take all of those tokens, you store them in an alphabetically sorted list. You can see here we have winter. It occurs exactly once in the document 1. So this here would be document 1. And in document 2, you can see, I don't know, ours is the Fury, and we can see Fury appears once over all our documents, and that is in document 2. And you can see is, for example, appears in 3 documents, and those are 1, 2, 3. So if you search afterwards for an HTTP verb, a response code, just error, you don't have to run grep against the full batch of text or logs that you have collected, but you go into that terms dictionary, you search for error, you see how many times it appears, and you basically have a pointer into which documents or log lines, more or less, where those appear. So you then have that pointer. That's why this is called an inverted index, because from the search term that you have extracted and you're searching on, and since this is alphabetically sorted, this is very fast. You just have the pointer where those appear, and that makes your search very fast afterwards. You have the similar data structures for numeric data types, for IP addresses. All of those are extracted and then readily available to search in a different way. So you will have different data structures in the background that are created, which obviously has the downside you need to spend the time to create those data structures. And additional data structures mean more disk space, because we store data potentially multiple ways and in multiple of these data structures in the background, just to keep access to them pretty fast. So for example, there's one data structure for full text search, and another that's the inverted index, and the regular index or the uninverted index, that one would be the one you would use to do an aggregation or to filter on or to sort on the search. Because there you basically want, for the inverted index, you go from your search term to the document. And for these ones here, you basically say like, okay, these are the documents I'm working on and I want to have them sorted. So here you need to go the other way around, from the document to these terms you want to sort on or filter on, for example. That's why you have here, you would need 2 different index structures for different use cases. And of course, the queries are very different, because Elasticsearch has a JSON interface. So while you can run a regular expression against the data that you have extracted, and I could just have the entire log message and run the regular expression against that, that's not really where the power lies. Here you can see I have my, for example, my Nginx access log I search it, and then I provide the JSON document what to search. And then I say, I have a query. I want to match on the field user.id. I want to get all the log messages from the user ID Philipp. So I want to see everything that I have done on that Nginx web server, for example. And this is not going through all of the logs and then doing like a grep or any other regular expression. But this is then just going to the index structure, looking at those fields that we have extracted. Obviously, you can put a nice interface on top of that, and then you can search just for errors, and you have a timestamp, and you have like, okay, the log message. But that's just like the sugar on top. The problem here is that first you need to parse the data. So, I mean, we have parsers for known formats like Nginx access logs are common enough that we have the regular expressions to parse those for you. We also, for your custom applications, we provide a custom mapping basically, where we take from a log appender, we map things the right way for us. So we have like a schema, a predefined schema that we have defined and generally use everywhere. But you need to have that. And if you have a weird custom log format, you might need to write the regular expression yourself to parse that. And I will always joke that writing regular expressions is like the Stockholm syndrome. It's at some points you're getting so used to doing that you like it, but maybe not everybody likes writing regular expressions. And you know, the plural of regular expression or regex is regret, because stuff often goes wrong. The other downside here is that there's of course overhead. Like if we at index time prepare all the individual fields, we need to do more processing. And then we have all these additional index structures that we need to store on disk. And potentially we have more of these index structures in memory. So our search will be very fast afterwards, but it's much more expensive just in terms of compute and disk and memory. So if you have terabytes and terabytes of logs, you might need quite a bit of more hardware, which can be a pain point. Or you're just like, oh, I want to find my logs so quickly. So in 3 seconds, I want to have terabytes and terabytes of data searched. Maybe I'm willing to pay that price in hardware just to run those searches so quickly. So that's kind of like the trade-off that you have here. And one of the next or newer solutions then is Loki from Grafana, which is taking a bit of a different set of trade-offs. And I don't want to say it's going back to the grep approach, but it is trying to find a slightly different middle ground here. So it has maybe intimidating architecture, I'm not sure, but it has like a write path where it has kind of like optimized of like, how do you split up the data and write it in a scalable fashion and also compact it and combine like the right pieces of information into the right so-called chunks to then make querying easier. So the thing about Elasticsearch is, since it's coming from full text search, and I don't want to say it's like accidental that it ran into logs, but it's more like, okay, you can put logs into this general purpose data store. Loki, on the other hand, was specifically built for this logs scenario. So there are very specific trade-offs built into that architecture of how you store the data. And you have basically an index of some of that metadata. And then you have chunks, which is the actual logs that you have collected. And you basically, the trick here is that you try to combine things that you want to search together. You will try to put in a same chunk. And then you can run a regular expression much more efficiently on that subset of data. And you can also put a lot of that data on like an object store, like S3, for example, to keep the cost much lower. So you don't need an actual EC2 instance or whatever running to search your data, or you still need those, but you don't need to keep all your data on those because you can keep some of those chunks that you want to search on a blob storage, just to keep that simpler. And just to give you an idea of like how you can structure data, you can say the component I'm taking a log from is a printer, and then you have a specific location, and then you have a log level, and that is a so-called stream ID. And everything with that same stream ID, which is basically this information hashed together, will be stored together. And then you have in the chunk of that stream ID, you have the actual log messages combined. And now when you search and you can say, oh, I want to have all the errors from this location, or I want to get all the messages from printers or whatever, based on this metadata, you can basically have a good subselection of the right chunks. And then you can run a regular expression or a grok against just the right chunks. So it's kind of like preparing the data in a, excuse me, you can prepare the data in a smarter way, so that you can work on that. The downside is if you have like this structure wrong, searching across that will be much more expensive or more complicated. But it allows you to kind of combine similar data together in one chunk, and also do much more around compressions and just keep the total cost of ownership in terms of hardware much lower. Though you might trade some features there, because here you're back to regular expressions then, and you will probably, or you will also trade some performance. So if you have like a good sub-selection, on modern hardware, you can run a crazy amount of regular expressions against text in a pretty reasonable time nowadays. And you can see if I keep the same component and location, but change the level or the log level that I have here, that would create a different hash. So that would go to a different chunk. So if you know, like I'm only looking for errors, you know exactly which chunks to target. If you search for error and info, you would need to search multiple chunks to get to that information, or depending on what labels you have extracted. So Loki is also very good or very well built around assumptions in Kubernetes, and like what kind of metadata you have and what is like common to filter. So for example, you might just search through the logs for a specific namespace or pod or whatever. So finding those right keys to structure your chunks is kind of a big part of the trick. But you don't have to structure your other log messages. You just dump them right in as you have them. So there it's kind of like a very different trade-off to both what Splunk is doing, but also how Elasticsearch is approaching that. So by picking different trade-offs, you can switch the problem to be very different or optimized for a specific scenario. And the queries then can look something like this. So this here is basically a job. MySQL contains error. Something with the name Kafka has the regular expression, and then you match on this regular expression. Or here in Cassandra, you also match this regular expression where you have error equals, and then whatever other word comes after that. Those are 3 sample queries that you could run in Loki, which again, kind of reminds you of what we have seen in Splunk before or in grok before. Whereas the Elasticsearch query syntax, because it's also much more highly structured, is very different. So it's kind of like a very different set of trade-offs or assumptions built into those. So this is optimized for a specific use case, and also because it's much younger, not as feature-rich, but that's kind of like where they are trying to catch up right now. And what I want to, as the final point, kind of like dive into, and I'll be finished in 3 minutes or so, is like the convergence of the different solutions to kind of like try to pick the best of the other solutions. So for example, in Splunk, you can structure your data more strictly, so you have faster search afterwards. In Elasticsearch, we have very recently added something we call the runtime feeds, where you basically store something and you extract more information at query time. So rather than doing all the work up front and extracting all the fields, the queries will be a bit slower, but you don't need to do that work up front, and you don't need to extract it and store it in specific fields or in multiple ways. You do more at runtime. So you kind of like get the benefits of that. Or for example, if you figure out you want to answer a specific or a different type of question and you need to do that at runtime, that is what runtime fields would allow you to do. Loki is also trying to add more features, whereas in Elasticsearch, we're kind of trying to go the other way. So in Elasticsearch, since we have all those features and it's like very feature rich, but that makes it a bit expensive sometimes, we try to reduce the features we have on by default potentially. So while we can have all the features, it's maybe too expensive to have all of them turned on by default. So we might not extract all the pieces of information, or we might not index them in all the different ways that give you all the different access patterns, but just optimize for specific access patterns and then do more stuff at runtime, which will then make your queries slower, but it will make your overall solution cheaper. So that is kind of like an optimization. Or just to give you an idea, because this is like the result you could get from Elasticsearch. I hope this is kind of large enough to read. So this is the access log that we have seen before, and it has a timestamp. And you can see we have extracted all of those different fields, and then we have here the message. And you can see we have also extracted the get. We have put that into HTTP request method get. So it is nice, so we can just filter down on that get. But it's also expensive because we have like all these additional fields and it makes the message larger. Also, we have a lot of metadata. So we always store the index and the type and a very large ID, especially if you have like a very short document. Just that large ID, so if you just have a very short log message, just that large ID might add a lot of overhead. Like it might make your logs 20% larger than without that ID that you don't really need, just because as a general purpose data store, everything has an ID, but do you really need that? And we are currently working on optimizing that. So we might be able to get rid of the ID. And then especially for short log messages, that would save you a lot of disk space right away, or have various other optimizations in store. Also, I think generally competition makes you sharper or better as a product. So when we saw, for example, that Loki is very fast at grep, we added another data structure to potentially make grep faster in Elasticsearch, if you want to do that. Or we have something called searchable snapshots now, which also allows in Elasticsearch to store data on S3 rather than actual EC2 nodes, for example. Also to keep the cost down a lot and just keep terabytes and terabytes of data on S3. Search will be a bit slower, but it is a cheaper solution. So I think everybody can kind of learn a lot from their competition. And it's a bit like converging and finding the right feature set or combination. So to wrap up, this is not a benchmark. And I'm generally very careful around benchmarks because it's often this benchmarking where you find similar conditions and then something is very good for your solution and very bad for the other solution. And then you basically kill the other solution. So benchmarks only make sense for your scenario and your requirements and your hardware and your write patterns and the amount of data you have and everything. But the general discussion I hope we can have now to some degree is, what is the right trade-off between the features you want to have, the speed you require from your logs, and the cost you want to pay? And obviously, you want to have all three, but it's not possible to have all three. It's kind of like a trade-off and finding the right combination between all three of them. And that's kind of the idea here. And that's it. Do we have any questions?